So last time we built our own backpropagation engine using which we could define variables on which we can do backpropagation. Now let's use this engine that we have built to create our own neural network from scratch. So the most fundamental unit of a neural network is a neuron. So mathematically, neurons are very simple. They just take in a few inputs along with some bias term and then output a single value. So this will be input 1, input 2, input 3, and these essentially can be the features that your model that you want to build a model on. Along with the bias term, they get multiplied and then out comes a single value. So let's define a class for this neuron first. So I'm going to call this class neuron, and upon initialization we need to know how many inputs are there in the neuron. So input size is required, and those number of weights are required in this neuron. So every input gets multiplied with a weight and then with the bias term, added up with the bias term, and then out comes the single value. So we need to define these many weights. Now this unit is what we were using previously for our backprop engine. Now how do we initialize these units? So in neural networks, you initialize these units with small random values between 1 and -1. So those are our weights. And finally, we need a bias term. That will also be a unit, which will also be randomly initialized between 1 and -1. So that's our initialization. After initialization, we need to define what the method is going to be when we call this neuron. So let's define that. Now this call is made with some inputs. These are nothing but I1, I2, I3 features that we just depicted over here. So when you call this neuron, it should multiply the weights with the individual features in the input and the weights, and then it should add the bias term to it and then return the output. So very simple. If we had to write this expression mathematically, it will be nothing but I1 multiplied to W1, then I2 multiplied to W2, and so on, and then finally adding the bias term, and this will be nothing but the V that we have defined over here. So that's the neuron class. Now that we have our neuron, a neural network is made up of multiple of these neurons stacked on top of each other in a layer-like structure. So let me explain that a bit. So suppose we have these same inputs I1, I2 and I3. These would go into a layer of neurons like this, and these neurons will then feed into the next layer and then the next and then the next until you reach the output layer. So let's say that you have another layer of neurons in the middle, and all of these neurons then feed into the final unit. So let's build a class now using this neuron class to build these layers of neurons. Now we build a class for this. All right. So let's call that class also layer. Now when initializing this layer, now we need to know how many of these neuron units do we need? So let's call that num neurons. And we'll initialize those many neurons with what input size? So the initialization of the layer takes in the input size, which is nothing but the size of the input that you want to feed into the network and the number of neurons that you want in this layer. Now when somebody calls this layer, we need to compute an output. So you will get some input, and this input gets fed into each neuron, and then you return back the output of that. So output is nothing but calling neuron with these inputs for all the neurons in the layer. So self.neurons, let's call it neurons. And then we just return this output. So that's a layer. Now that we have our layers, which are built up of multiple neurons, we can finally build a neural network which will be made up of multiple layers. So let's go ahead and define the neural network class. Let's call that NN. Now, while initializing the neural network, all we'll need is the sizes of these layers. If you noticed, the size of the current layer depends on the output size of the previous layer. So for this first layer over here in our diagram, the size is nothing but 3 because 3 inputs are coming into this layer. For the second layer also, the input size is 3 because of the number of inputs coming from the previous layer. And finally, for the last layer, our input size is also 3 because 3 inputs are coming from the last layer. So let's define the layers here. Now, we'll go over the layers, sizes for these layers. Let's start from the first position because we know the first size is nothing but the size of the input, and let's append our layers to it. So let's define a layer. So for this particular layer, the size of input is nothing but the output of the previous step, so that is I minus 1, and input number of neurons is nothing but the current size. So that's our layer, and when somebody calls our neural network, we need to compute the output by going through all of these layers. So we'll get some input vector, and for every layer in layers, we'll update this input vector by calling this layer with the input vector, and then finally we'll return that input vector. So what's happening is we take this input vector, let's in our case which is I1, I2, I3, call this first layer using these inputs, then we call this second layer using the output from the first layer, and then call this third layer using the output of the second last layer. That's what we are doing with this loop. Before we initialize a neural network, we'll need a way to collect all the parameters in our network. The parameters are nothing but these weights and bias terms. So let's go ahead and define that. So for a given neural network, let's say we'll have a parameters method, which we can call to collect all the parameters. Now this method in turn will call the parameters method for every layer. So for layer in self.layers, it will call the params method for each layer, and then finally return all the parameters. So we now need to define dot parameters for every layer. So let's go back up and define that for a layer also. Now this parameters method will call the params method of each neuron. So for neuron in self.neurons, similarly it will extend the params list with all the neurons by calling parameters method on it, and finally return the parameters. And finally, when we go to neuron, this will also have a parameters method, and this will return nothing but all the weights and the bias term. So this will return weights and the bias term as a list. So what's happening is every neuron is getting called with dot params on it. So this will return a list of weights and biases in that neuron. In each layer, all such weights and biases are collected, and then at model level, all of the layers are collected, and that will finally give us all of the parameters in our model. Now let's go ahead and initialize a simple model. So let's initialize a model with size, let's say 2, 3, and 1. I think we have to rerun this. And finally, let's initialize the model. Yeah, so our model is initialized. It expects two floating point inputs. So you can push a value like 0.9, 0.8. So these are the two inputs that the model expects. I'll return a one single value as output. Yeah, so it returns one unit value as final output. Alright, now that we have our model, let's go ahead and generate some data and train it. So I'm just going to copy paste some code to generate data. So this is the data on which we want to train our neural network. Essentially, the neural network should be able to separate these two classes from each other. And since our model expects two input, we are giving input as the x and y axis values. So x's are nothing but the x and y values in this two-dimensional plane, and y's are two classes. So it can either be -1 for the blues and +1 for the reds. Let's go ahead and define a trainer. So the trainer will take x and y as input and the model, and for how long do you want to train the model, so we'll call that epochs. So let's initialize that as 10. And what should be the learning rate? So let's initialize that as some really small value. So now for epoch, in range of epochs, so these many times we want to train our model. For every epoch, we'll go over all of the training data. So we'll zip over x and y and go over every data point. For every data point, we'll get some output from our model. So we'll push xi and we'll get some output, and we'll get a loss. So loss will be nothing but how far off we are from yi. So the output. So this over here is called a max margin loss. So if you look it up, max margin loss. So it's also called hinge loss. It's primarily used in algorithms like SVM. It gives you an idea of how far off you were when predicting from a neural network. So the formula is very simple. It's just 1 minus the y, that is the actual prediction, and t, which is a classifier score. So our classifier score is nothing but the model is outputting, which is out, and yi is nothing but the real value. So that's our loss. And let's declare loss as well. So we collect all of these losses, and then we say that the total loss is nothing but sum of all of the losses over all of the data points. So this sort of gives you the average loss for the whole epoch, right? And like we discussed last time when talking about gradient descent, we will set the gradient for this loss as 1 and then call the backward method on it, dot backprop. Let's see what we named it. Did we name it backprop or backward? Yeah, so we named it backward, so we'll call backward method, right? Now that we have called backward method, the gradients would be filled into all of the units that we have initialized, and we can now make a gradient step. So over all the parameters in model.parameters, so these parameters are nothing but the weights and biases. Now we need to adjust these weights and biases. So for those parameter dot data, we need to update it by taking a small step. So that step size is nothing but the learning rate in the step size in the direction of the gradient. So parameter dot grad. So we take that gradient, take a small step towards that step's direction, and then update the parameters data accordingly. So for every parameter we do that, and after doing that we can now reset the gradients back to 0. So again we go over our parameter in model dot parameters, and then we can reset the gradient back to 0. So that's our simple training loop. Let's do one more thing. For each epoch, let's print out what are the different things we want to track. So let's print out the epoch number. Let's print out the total loss, and let's also print out the current accuracy. So accuracy is nothing but accuracy. Let's define this accuracy also. Let's just use sklearn for this. So from sklearn.metrics we can import accuracy score. An accuracy score will take nothing but the actual values, so the actual prediction, the actual labels, so that's y, and our predictions. So let's define predictions also, and we'll say predictions are positive if the output value that we are predicting is positive, else it is negative. So if it predicts a positive value, that means it's predicting a positive class, otherwise it's predicting the negative class. So that's our simple trainer. Now let's go ahead and use it and train the model. So we'll call our trainer to train the model. So the trainer takes in the x value, the y values, which are our labels. We'll take the model as input and the number of epochs. So let's say we'll train for 10 epochs and our learning rate would be 0.5. Alright, as you can see, the loss has decreased. So we started with 77% accuracy. We're up all the way to 83% accuracy. Let's go ahead and visualize the decision boundary that the model has learned. I'm just going to copy paste some code to visualize the decision boundary. So this is the boundary that the model has learned. Ideally, we would want the model to squiggle in between these small points and separate the two classes almost perfectly. So let's do that. Let's increase the model size and see if it can do that. So I'm just gonna say that the hidden layer size, will increase the hidden layer size from one layer of 3 neurons to 2 layers of 6 neurons each. So let's initialize that. The input and output remain the same. Let's go ahead and retrain this. All right, so we can already see that our accuracy is a little bit better. So we are now at 87%. Let's train a bit further. I'm just going to reduce the learning rate a little bit. All right, we're up to 92%. So let's see what the new decision boundary looks like. So let's run it again. Yeah, so as you can see, it is trying to squiggle in between and find a new decision boundary, which is not better. So you can increase the number of parameters in the model and eventually learn a better model just by increasing the number of neurons in each layer. All right, so that was neural networks. Thank you.